Hey everybody, welcome to 2.5. Today we are looking at real solutions of polynomials. You are going to want a calculator. You can use a calculator. You can use the Chromebook TI calculator app, or you can use the Desmos website. All of those are appropriate. For this video, I am using a app that's almost exactly like our calculators. Will be a few things different, so bear with me on that. First things first today, roots, zeros, solutions, x-intercepts. All of those words mean the exact same thing. They are the x value at which y equals 0, and where the graph crosses the x-axis. Now, a y-intercept is the y value at which x is 0 and where the graph crosses the y-axis. Now, none of that is earth-shattering, but we do want to remember where the coordinates, how the coordinates relate to this. So when we're talking about an x-intercept, we want to keep in mind that the y really does equal 0. Now, something that may be a little new, relative extremes. These are going to be points on a graph, and these relative extremes are points that are either a max or min on an interval. Meaning, given a specific piece of the domain of the graph, and relative extreme will be a max or a minimum in that interval. So if we're talking about local maximums, a local maximum is going to be the highest point over an interval. Given a specific piece of the graph, it's the highest point in that piece. And then a local minimum is going to be the lowest point. That looked weird. It's going to be the lowest point over a specified interval. Okay, so a relative extreme can be generalized a little bit just as a peak in the graph. A local maximum will be a high peak, and a local minimum will be a low peak. And we'll look at some examples of those on the graphs below here. Now, let's talk a little bit about some specifics with zeros. The number of zeros a polynomial has is the same as the degree of its polynomial. Degree being the highest power of x. But some of these zeros may be real, some may be repeated, and some may be non-real, or what we call imaginary. Okay? A single zero or a single root will look like something just going clean through the x-axis. Okay? It just goes through the x-axis. Nothing funny, just through the x-axis, pretty plain and simple. A double zero looks a little bit like a quadratic. Double, power of 2. What happens with that is that we have a bounce. Okay, we have a bounce. So a double zero is actually tangent to the x-axis, meaning it touches it but doesn't go through it. Okay, so a double zero has a tangent bounce, also known as a tangent double root bounce. It's a tangent double root bounce. A triple zero comes from a third power situation. And a triple zero, I have a hard time drawing this sometimes, forgive me, kind of zigzags through the x-axis. So a triple zero will zigzag through the x-axis, much like the parent function of x cubed, y equals x cubed. Then a non-real solution on a graph may look something like this. And if you notice, it's a big deal. It actually does not cross the x-axis. So those are our possibilities. Well, there's more, but those are the possibilities we're going to study. Single roots go clean through the x-axis. It doesn't have to be straight, but there's no bouncing or curving or zigzagging. A double zero will be a tangent bounce. A triple zero will be a zigzag. And non-real won't cross the x-axis. So if we look at example 1 here and all of these little questions after it, it's not that intimidating, I promise. Don't be scared. Looking at this graph. Okay, the degree here is odd. Okay, the degree here is odd because the left and right ends, left and right go opposite directions, meaning one goes down, the other goes up. Okay, this is a positive leading coefficient. It's a positive leading coefficient because the right end goes up. On the right side, we're going up. Okay, now the number of zeros here. Okay, the number of zeros here is every place the graph crosses the x-axis. So there's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 places the graph crossed the x-axis. So that is 5 x-intercepts. And it says list them. So when there's multiple x values, we need to get used to this notation. X equals, use the curvy braces, and it's A, C, E, G, and I. Use the curvy braces and separate the values with commas. You'll see that notation a lot. Okay? Now, the number of distinct zeros, distinct means different from each other. All of these are different from each other. There's no other situations in this graph. Number of single zeros, all of these are single. They go clean through the x-axis. There's no bouncing or zigzagging at the x-axis. So all 5 of these happen to be single zeros. So A, C, E, G, and I are all single zeros. Okay, there's no double zeros, and that takes care of all the zeros here. Okay, the y-intercept here is point F. F of 0 is whatever that value of F equals, meaning 0, F is the ordered pair. We're going to use that here in just a little bit. Now, the number of relative extremes. Relative extremes are high peaks and low peaks. So we have a high peak, a low peak, a high peak, and a low peak. So we have 4 relative extremes, and they are at B, D, F, and H. Those are not solutions, so we don't need an x equals and the braces on those. We can just list them. Okay? Now, specifically the local minimums would be those low points. So that's going to be D and H. There's two local minimums, D and H. Okay, then the local maximums will be those high peaks. B is a local max, and so is F. There's two of them, B and F. So I think from this picture, you can get a better idea of what local min and local max mean. It's a maximum for that location on the graph. It's a minimum for that location on the graph. The degree of this polynomial is 5 because there are 5 distinct zeros. Okay, number of zeros, the degree of that polynomial match. So let's look at the second one. And let's look at its degree, being even or odd. Okay, its degree is also odd, again, because the left and right side point opposite directions. One is up, one is down. The leading coefficient here is negative, and it's negative because the right side, the right end of the graph goes down. Means that leading coefficient was negative. Okay? Now, the zeros here. There is a 0 here at A, at C, and at E. Okay? At A, at C, and at E. Okay? Now, if we look at these really carefully, at A, we have that tangent bounce. A is a tangent bounce. So it looks like, because of that bounce, that counts as 2 roots. The point at C here is a single, just goes clean through the x-axis. And E is another place where we have a tangent bounce or a double root bounce. So that also counts as 2 roots, 2 degrees. Okay, so the actual number of zeros here is 5, but there's 3 x-intercepts, and they are at A, and at C, and at E, and that needs the x equals and the curvy braces there. Okay, those 3 points are zeros. Okay, the number of distinct zeros is 3. The number of single zeros is 1, that is just point C. There are 2 double zeros, and those are at A and at E. A and E have double zeros. The y-intercept would be here at point B, so G of 0 equals B. The relative extremes here, we have a low, we have a high, we have a low, and we have another high. So that makes 4 relative extremes. And those are at A, B, C, and E. A, B, C, and E are all relative extremes. Okay, local minimums, there are 2 of them. That tangent bounce at A is a minimum, and the point at D is also a minimum. There are 2 local max, and those would be at point B and at point E. Okay, that's a high peak for that region of the graph. Now, the degree of this polynomial is going to look a little bit different because there's 3 zeros, 3 solutions, 3 x-intercepts, but this is actually a degree of 5. And it's a degree of 5 because there are 2 doubles. There are 2 double that count as 2 each, and one single that counts as 1. So that adds up to a degree of 5. Now, let's look at an example. Let's look at example 3. We have factored form of an equation. It's asking for its degree. We have an x multiplied by an x multiplied by another x. So that is a degree of 3, and there will be 3 total solutions. Now, we can find these solutions without graphing this. And we find the solutions from the factors. Set each factor equal to 0. And so x will equal, we do need the curvy braces there, x will equal -1. If we set x minus 2 equal to 0, we get x equals 2. Setting x minus 4 equal to 0, x would be 4. So there are 3 x values, -1, 2, and 4. Now, to find the y-intercept, f of 0 means 0, y, meaning we can plug in the 0 for x. So plugging in that 0 for x, it feels a little weird to plug this into factored form, but it can be done. So if we plug in that 0 for x, 0, 0, 0, and work out what that y value equals, that's 1 times -2 times -4, it's going to be positive 8. So that y-intercept here is positive 8. Okay? Now, we want to sketch the graph, and we can actually do this without the calculator. So we know it has a y-intercept of 8. We just found that. We know it has an x-intercept at -1. We know it has an x-intercept at 2. And we know it has an x-intercept at 4. And we have to connect the dots a little bit here. Now, something that helps is we know that a degree of 3 is odd, meaning one end will point up, the other end will point down. We also know that in the factors, there were no negative coefficients. So the leading coefficient here is positive. So we have a lead coefficient that is positive, and we have an odd degree. So that's enough to get a general sketch. Leading coefficient being positive means the right end goes up. So from this furthest right 0, we have to go up. Okay, meaning we would have to come down but come back up through 2. We have to go through that y-intercept, and then we'd have to come back down through that -1. And this makes sense because we do have one end pointing up, one end pointing down. Now, you can type that in your calculator, verify that with a graph. It's not perfect, but that's the general shape of it. So let's look at example 4, and let's talk about what changes. This power of 2 is the difference between example 3 and example 4. Okay, so this changes a little bit. In this problem, it changes the degree. There's still what looks like 3 powers of x being multiplied, but this is actually a power of x. The second parentheses is actually a power of x squared. And then that third parentheses is just an x. So this is a 4th degree, and there's going to be 4 solutions total. Now, again, without graphing, what are those solutions? Those solutions, curvy braces, x equals curvy braces. That first one, x plus 1, set it equal to 0. We get x equals -1. This next one looks a little different to begin with. X plus 2 all squared equals 0. Do not expand that. Do not square that out. We're solving for x, and there's already only one x in the problem. take the square root of both sides. So that means x minus 2 equals 0. So x equals 2 is a solution. It's just 2. It's nothing else weird. Then x minus 4 set equal to 0 would give us 4 as a solution. So that looks like there's only 3 solutions, but we have that squared factor. We have that squared factor. So that squared factor is going to lead us to a double situation, which counts as 2 roots. Now, this next calculation is going to be a little different from the previous example. We're looking for the y-intercept. So again, we're going to plug in x equals 0. And this time, we do have that squared factor. So when we plug in that 0 for the x, we still have 1. But now we have negative 2 that's squared negative 4. Well, negative 2 squared is positive 4 times negative 4 is a negative 16. So we have a y-intercept this time of negative 16. So we can already kind of tell this graph's going to look different. Our y-intercept way down here at negative 16. Okay, now we have the same x-intercepts we did before. We have an x-intercept at negative 1, we have an x-intercept at 2, and we have an x-intercept at 4. Okay, now the difference here is that now we have an even degree, and we still have a leading coefficient that's positive. None of those x's had a negative number multiplied by it. So we have a leading coefficient that is positive. Both ends will point the right end will point up. And we have an even degree. So both ends, left and right, will point the same direction. They'll both point up. Okay, so from the 4, on the far right, we point up because that leading coefficient is positive. From the negative 1 on the far left, we also point up because it's an even degree and those ends have to go the same way. Now, what we have to note here is that this root of 2, because it was squared, it is a double root, meaning the graph is going to bounce there or be tangent. So if I start right to left backwards, I'm going to start over here on the far right. Actually, I'm not. I'm going to start here on the left. We're going to go left to right. From negative 1, I have to go down. I have to go through that negative 16 y-intercept. When I get to the root at 2, it's the double. It's the tangent root. So it's going to touch the x-axis and bounce back. And then we're going to go up through the root of 4. Okay, this root is a tangent double root. It's a tangent double root, so the graph bounces off the x-axis there. It doesn't go through. Now, you can verify that by graphing it in your calculator. It'll look roughly like this. Okay, so if you compare the graphs on example 3 and example 4, you can definitely see what effect that tangent root has on the graph. Changes the degree, it changes the directions, changes that bounce on that double root. Now, let's look at getting given some graphs. Let's write some equations. So let's look here at example 5. We have a graph of f of x shown. Okay, the left end and the right end both point up, so that's an even degree. The right end is going up, so that is a positive leading coefficient. The y-intercept is at negative 2, meaning f of 0 equals a negative 2. We're going to use that here in just a minute. The number of real roots the number of real roots. We have a root at x equals 3. That is a single root. Graph goes through the x-axis. At x equals 2, we have a tangent double. It's a bounce. It doesn't go all the way through the x-axis. It touches it and bounces back. And then we have another single root at x equals 5. Okay, so there are 4 real roots, 2 singles that are counting as 1 each, and then 1 double that counts as 2 each. So that really is a total of 4 roots. Now, we want to write these equations in factored form. And what factored form looks like, believe it or not, that said factored form. Factored form is f of x, or y equals, there's a coefficient a, the leading coefficient a. Then x plus or minus one of the roots, x plus or minus another root, and so on and so on. However many roots we need, we'll use, okay? And that a in front is that leading coefficient. And that's what we're going to look at finding right now. So what we need to do is figure out the factors. So f of x equals a times, we have a single root at x equals -3. So that factor had to be x plus 3. We have a tangent double root at x equals 2. That factor was x minus 2. And because it's a tangent bounce, it's squared. And then we have a single root at x equals 5. X minus 5 is that root, that factor. Okay? Now, in order to find the a, we use that y-intercept. Okay? f of x has that a coefficient, and in order to find it, we use that y-intercept. When the f of 0 is -2, 0 is x, -2 is the y, so we can plug that in and solve for a. And that's what we're about to do right here. So we will plug in a 0 everywhere there was an x, and that answer will be -2. And I'll get the rest of the equation on here for you. A is what we're trying to find. 0 plus 3, 0 minus 2 all squared, 0 minus 5. So -2 will equal a times 3. -2 squared is 4 times -5. 3 times 4 is 12 times -5 is -60. So -2 is -60 times a. So a is 2 over 60 or 1 over 30. So when we write this equation, f of x will equal that 1 over 30 times x plus 3 times x minus 2 all squared times x minus 5. And this is our function. Pause just a second and graph that in your calculator and verify that it matches that graph above. It worked, didn't it? Because I know you paused it and checked that. So let's take a look at the next one. We are looking at this graph, looking for its degree. Left end points down, right end points up. Those are opposite. That makes it an odd. The right end does point up, which does give us a positive leading coefficient. Now, these numbers are really hard to read. These numbers are really, really hard to read. That y-intercept is negative 12, meaning g of 0 equals negative 12. Okay? Now, on these roots, we have a root at x equals negative 3, and that is a tangent root. That is a tangent double because it bounces off the x-axis and comes back. At x equals 2, we have a single. So a double and a single add up to 3 roots. 2 for the double, 1 for the single. 1 single, 1 double. And again, we want to find the a value, that leading coefficient. So we start with f of x equals that a value. That root at x equals negative 3. X plus 3 is the factor. And since it's a double root, it's squared. X equals 2 is a single root. So that factor is x minus 2. To find the a value, we use that y-intercept. So we will plug in, there we go. We will plug in 0 for x, and we'll get negative 12 for that y value. So negative 12 will equal a times 0 plus 3 all squared times 0 minus 2. So negative 12 will equal a. 3 squared is 9 times negative 2. So negative 12 equals negative 18a. Divide by that negative 18. Negative divided by negative is positive, and reduce that fraction, and we get a equaling 2 over 3. So this function, f of x, will equal that a value, 2 over 3, times the factor x plus 3 all squared, times x minus 2. And this is your function. Go ahead and pause and graph this in your calculator. Double check that it gives you what we had above. All good? Now, this next piece of the lesson is where you're going to want a graphing calculator to start this process, okay? The app I'm going to project on this tablet is a little different from your calculator, but very, 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 very similar. So, what we want to do is graph, in our calculator, graph this function. Remember, f of x is just another way of saying y. So we'll go to y equals. We will put the equation into the calculator, and we will graph it. We're going to look at the total number of zeros, and we're going to sketch that graph. So what is the total number of zeros here? X to the third is the highest power of x. So this is a third degree polynomial, degree of 3. Now, to sketch the graph, like I said, we're going to go to the calculator. I have this typed in the calculator. It's that first one. X to the third plus 41x squared minus 9x minus 14. And I'm going to graph this on a standard window. Okay? Now, we can't see all of this, but what we can do is look at where those x-intercepts are. Okay? Now, I'm going to go back to y equals, and I'm going to make another line, y equals 0, and graph it. Reason we do that is we want to find those solutions. Solutions are where the y value is 0. I can go to second graph and go to the table, and I can go to where y is 0. And we see here that we do have a root at x equals negative 7. As I go through the graph, the table, I'm not seeing the other x values that make the y 0. So what we do know for sure is that we have one root at x equals negative 7. Okay? Now, there's a couple more. 2 more to be exact. We look at this graph. We see 2 other places where that crosses the x-axis. To find it, make sure you have another equation in the calculator, y2, that equals 0. And to find that intersection, do second trace, intersect. On your calculator, you will hit enter, enter, and then scroll to close to the solution. Okay, on this one, I have to scroll over a little bit first. Where am I? Okay, so scroll close to the root, second trace, enter, enter, scroll, enter. Okay, now if you look at the bottom of your calculator screen, it will give you the word intersection, and it will give you the x coordinate, and it will give you the y coordinate. That y coordinate should be 0. Okay, so x is negative 0.5. There's another root, negative 0.5. Now, we don't want decimals. We want the fraction. So we're going to write that as negative 1/2. Negative 1/2. Now, we still have one more root. We're going to do the same thing. On your calculator, you'll go to second trace, intersect, enter, enter, and then you are going to scroll close to that third root on the far right and hit enter a third time. Your calculator steps, second trace, intersect, enter, enter, scroll, enter. Scroll left, right. Okay? Now, this one, the x value, intersection, look for the word intersection, 0.666 repeating, y equals 0. That's the fraction 2/3. So this root on the right is at 2/3. Okay? Now, we know it's an odd degree. It's a positive leading coefficient. The right end will go up. And we come down and around, and here's our graph. It's not perfect on my paper, but if we look at this on the screen, I think I can pinch this. Maybe. And kind of see that shape. Okay? Now, that's the calculator part. Okay? Now that we have this graphed, okay, we see that there are no double zeros and there are no non-real zeros. We see all 3 solutions. Okay, we see all 3 solutions. Now, the x-intercept, remember the y-intercept, is where x equals 0. If you look at this equation, every term with an x zeroes out when you plug in a 0. So that y-intercept is just the constant. It's negative 14. If you plug in 0 for x, every term with an x is going to zero out, leave you with just the constant. Okay? Now, we already found the zeros. They were negative 7, 1/2, negative, and 2. Let me just write these down right properly here. X equals, use the curvy braces. We had a negative 7. We have a negative 1/2. And we have a 2/3. Those are the 3 solutions. Okay. Now, to write this in factored form. F of x equals, there is a value of a that we'll have to determine. And we know one of those factors to get a root at x equals negative 7, x plus 7 had to be a factor. Now, these other 2 roots are fractions, and they're going to be a little different, okay? To get an x equals negative 1/2, we want the factor, but we don't want the fraction. So what we do is we multiply both sides by 2 to clear the fraction. So we get 2x equals negative 1. Then we still need one side equal to 0, so we add the 1 back over. 2x plus 1 equals 0. 2x plus 1 is how we need to write that factor. Now, we're going to do it again with that third root. As soon as I can get this to move where I have enough room to write it. Not that far. So, we have x equals 2/3 as one of our roots. That denominator of 3 we want to get rid of. We'll multiply both sides by 3. So, 3x equals 2. Then make one side equals 0. So 3x minus 2 equals 0. 3x minus 2 is the other factor. That's how you handle roots that are fractions to get their factors. Now, we do need to find this a value. We do need to find this a value in factored form. So when we plug in x equals 0, that y is 14. So plugging in that negative 14, that's a. X plus 7, that's actually going to be a 0. And then 2 times 0 plus 1. Then 3 times 0 minus 2. So we need to watch those coefficients a little bit. Okay, so we'll get negative 14 equals a times 7. 2 times 0 is still 0 times 1. 3 times 0 minus 2 is negative 2. So negative 14 equals negative 14a, meaning the value of that a is 1. Use the y-intercept to find that value of a. Now, our function, then with that a, that leading coefficient of 1, is just x plus 7. 2x plus 1 times 3x minus 2. And again, go ahead and take a second and graph that in your calculator. I want a different color. Take a second, graph that factored form in your calculator. Make sure it matches your original graph. Now, let's do this again. Let's do this again. Example 7. Different equation. We're going to look at the same questions, but with a different equation. The total number of zeros of this polynomial is 4. Degree of 4, total number of zeros is 4. Now, we want to look at this graph and sketch it. Again, mine's going to be a little bit different than yours. Y equals, I'm going to turn this one off, turn this one back on. Typed that equation in. We're going to go to graph. And this looks a little different here. This looks a little different. If you look at that root on the left, you see a zigzag. And that's what a triple root will look like on a real graph. Not on one Miss Seifert tried to draw by hand. This is what a triple root looks like. So that root on the left is a triple, and that root on the right is a single. Okay? If we go to the table, that root that was a triple looked to be around negative 2. And we can see that when x is negative 2, that y really is 0. So that really is a root. Okay? That other root looks to be between 0 and 1. But between 0 and 1, yeah, there's really not a y equals 0 there. So we're going to have a fractional root. So to find that fractional root, second trace, intersect. On your calculator, you will do enter. Hang on, I messed that up. I need to scroll where I can get to it. Second trace, intersect. You hit enter, then scroll close to the root you're trying to find and hit the third enter. Your calculator should say intersection on the bottom. X equals 0.333 repeating, that's 1/3. And y equals 0. So this root is at 1/3. So we had a root at -2. We had a root at 1/3. Okay, that root at -2 was a triple. It came down, it zigzagged through, and went further down. And then it's going to come back up through that 1/3. And there is a rough sketch of the graph. Okay, there are no double zeros, but there is a triple zero. Okay, there is one triple zero. Any non-real zeros? No, because this triple zero counts as 3, and this single counts as 1, which adds up to that 4 that it's supposed to. Okay, that y-intercept, it's the constant. It's -8. When you plug in x equals 0, everything will 0, 0, 0, 0 out except that -8. So that constant is our y-intercept -8. We already found the zeros. X equals -2 and a 1/3. Guess we could label that y-intercept there, -8. Now, writing this in factored form. We have one of those roots that is a fraction, 1/3. X equals 1/3 was our solution. Multiply both sides by 3 to clear the fraction. Then 3x equals 1. Move everything to one side of the equal sign. Make one side equal 0. 3x minus 1 is that factor. So f of x will equal a times x plus 2, which gives us the root at -2, and times 3x minus 1. Now, to calculate that a, we use that y-intercept again. When x is 0, that y will be -8. So -8 plugged in for the y, 0 plugged in for the x, and we can calculate this a value. -8 will equal a times 2 times 3 minus 1 is 2. Something's up there. This is a third power on that 2, on that root. And I messed this up too. 3 times 0 is 0, minus 1 is -1. This triple root, let's come back over here to this graph for a second. This triple root means that x plus 2 as a factor was raised to the third power. That triple root was to the third power. So 2 to the third power is 8 times that -1. A here equals 1. And that means our final function, that a was a 1. We have that x plus 2 factor to the third power times 3x minus 1. And this is your factored form. It's a lot of steps. It's a lot of steps. We're putting together a lot of things we've done recently. Now, example 8 is going to shift gears a little bit, different type of question. Okay, in example 7, we want to show with synthetic division that x equals 2 is a triple solution. So what we want to do is show that we can take that f of x, divide it by x plus 2 over and over and over and over again. So to show that, we see how many times we can use synthetic division and have it be a remainder of 0. So that original function started with a fourth power. We had all the powers, 4, 3, 2, 1, none. So no skips. So 3, 17, 30, 12, -8. Now, be really careful. X equals -2 is the solution. X plus 2 was the factor. So we're dividing by x plus 2. We change that sign to the -2. Whatever you're dividing by, you have to change the sign. Same as we've always done with synthetic division. Okay? Bring down the first number. Don't do anything else to it. Just bring it straight down to 3. Multiply by -2, -6. Add, we get 11. Multiply, -22. Add, we get 8. Multiply, we get -16. Add, we get -4. Multiply, we get 8. Add, we get 0. Now, believe it or not, we were expecting that 0. Because this remainder of 0 means x plus 2 is a factor, which we've known about that rule for a few lessons. Right now, it means that it's a factor one time because we divided out and got a remainder of 0 one time. Now, we're going to do this again. We're going to disregard the 0 and we're going to divide out again. Okay, that remainder was 0. It does not affect the problem. We basically got a whole number, a whole polynomial for the answer. So we can divide it out again. We're going to do the same thing. Divide out a -2. We're going to bring down this 3. Multiply -6. Add 5. Multiply, get -10. Add, get -2. Multiply, get +4. Add, we get 0. Again, we knew we were going to get another 0 because we knew x plus 2 was a factor again. So this being a 0 now means 2 times we have a factor. We're going to do this again. I don't want that. We're going to do this again. Until we don't get a remainder of 0, we'll keep doing it. -2. Bring down that 3. Multiply it to -6. Add to get -1. Multiply to get +2. Add, we get 0. And again, that means we have another factor of x plus 2. So 3 times x plus 2 is a factor. And do it again. Put that -2 on the outside. Bring down that 3. Multiply, we get -6. Disregarding that 0. Adding, we get -7. So this remainder is not 0. So not a factor again. Okay, that last division did not work. So we only have a factor 3 times. Now, writing the factored form from this process. Writing the factored form from this process. We know that x plus 2 was a factor 3 times. We know that x plus 2 was a factor 3 times. To get the other factor from this method, we use the last division that worked, which would be here. That 0 was the remainder. That -1 was the constant. That 3 is the x. So that's where 3x minus 1 comes from. And this is another way to get to that factored form. Okay. Now, if you compare that to what we got previously from the graph, it's the exact same factored form. And it's supposed to be. Lots of things relating and connecting here. Lots and lots and lots of things. All right, let's take a look at another way you might see that question. And that question is, how many times is 2 a root. So how many times can we divide f of x by x minus 2 and still have a remainder of 0? We're going to do it again and again and again. This time 2 is the root, so we're dividing by x minus 2, meaning we put just a 2 on the outside. It's the opposite sign from the factor. Okay? On the inside, we start with fourth power, third, second, first, none. So we're good there. 1, negative 4, 3, 4, negative 4. And we will bring down that first number, 1. Multiply, get 2. Add negative 2. Multiply negative 4. Add negative 1. Multiply negative 2. Add positive 2. Multiply 4. Add, we get 0. So right now, x minus 2 is a factor one time. It is a single root as of right now. We're going to do it again. We're going to disregard the remainder. Do it again. Bring down that first 1. Multiply 2. Add 0. Multiply, we get 0. Add, we get negative 1. Multiply, that's negative 2. We get another remainder of 0. So now this is 2 times. And we have a double root. So we'll do this again. Put 2 on the outside. Bring down. We get a 1. Multiply, we get 2. Add, we get 2. Multiply, we get 4. Add, we get 3. And if you're looking at that going, uh-oh, hang on, something's up here. Nope, it's not. It's good. So this was not a third time. This was not true a third time because that remainder was negative 3, not 0. So that means 2 times is how many times x minus 2 is a factor. Meaning when we write that problem in factored form, that x minus 2 has a power of 2 on it. Okay? And because this last division didn't work, we disregard it, and we go to the result of the last division that did work. That remainder is 0. That constant is negative 1. The x is 0. X squared is 1. So that factor would be x squared. We don't need that 0, minus 1. And this is factored polynomial. All right, guys, one more problem. Thank y'all so much. Well, one more type of problem. And we've done this idea already today, just rephrasing it a little bit differently. We're looking for a polynomial equation of lowest degree with a double root of 2. Well, if x equals 2 is a double root, that means x minus 2 is the factor, and it has to be squared. And single roots at 1/2. Well, x equals 1/2. So we multiply both sides by 2. So 2x equals 1. So 2x minus 1 is the factor. And then x equals negative 2/3. Multiply both sides by 3 to clear that fraction. 3x will equal negative 2. Add the 2. 3x plus 2 is what's equal to 0. So that's our factor. So our lowest factored form, f of x would equal that x minus 2 all squared times 2x minus 1 times 3x plus 2. And this is our polynomial. It has a double root and 2 singles. That's a total of 4. So its degree is 4. And for real now, y'all, one last problem. Same idea. We're looking for that polynomial of lowest degree. We have a single root at 1/3. So x equals 1/3 is the root. Multiply both sides by 3 to clear the fraction. 3x equals 1. Make one side equal 0. 3x minus 1 is 0. We also have a double root at -3/4. So x equals a -3/4. Multiply by 4 to clear the fraction. 4x equals -3. Make one side equal 0. 4x plus 3 equals 0. So this function would be f of x equal to 3x minus 1. That was a single root, so it's to the single first power, times 4x plus 3, which was a double root, so we square that one. And this is factored form. So lots of different connections made with everything we've done recently. Connecting all the factoring to the solving, to the roots, to the shape of the graph, and finding all the different pieces. All right, y'all, that is it